this talk. I'm going to talk about Cox rings, and in particular, I want to describe the Cox ring of an embedded variety, as is given by the title, and I will explain you something more in what follows. So this is joint work in progress, very in progress, with Luca Ugaglia and Cristobal Herrera. Let me start introducing what is a Cox ring. Okay, okay, so in what follow, I will assume X to be normal projective variety. I forgot to put over the complex numbers, just to simplify, and I will mostly consider smooth varieties. Anyway, you can relax a little bit. This projective is not necessary for the definition of the Cox ring, but I will stick to this for simplicity. Then let me denote by W div of X the group of veil divisors. This is a subgroup of principal divisors, and this is the divisor class group. It's the quotient between the two. So this is a kind of basic ingredient for defining the Cox ring. This hypothesis is fundamental, so the Cox ring is defined when the divisor class group is finitely generated. So you can translate this with the irregularity 0, basically, the variety. In that case, you can choose a subgroup of veil divisors which is finitely generated and such that the class map is a surjection. And you can construct this sheaf of divisorial algebras. So this object is a Riemann-Roch space. I mean, over an open subset U, they are rational functions such that the divisor of the rational function plus D is effective. Then you take the direct sum, and in this way you have an algebraic structure because you can multiply sections. If you take one of these in OX of D and then another one in OX of D prime, then the product, it's easy to see that it lives in OX of D plus D prime. So you have an algebra structure here, and basically, you do this construction, which is written here. This is not very important for us, but it's part of the theory, which is done, is introduced for identifying divisors which are linearly equivalent. So you want to take quotient, you just want a copy of one of these for each equivalence class. That's basically it. So what you do concretely, you choose a homomorphism from the subgroup of K. K is this guy, consisting of principal divisors inside K. Then the homomorphism goes to rational function, non-zero rational functions, and in such a way that this is a rational function. When you take the divisor, you get the original D. So you want an F such that div of F is the original D. And then for each D in this subgroup, you define an ideal sheaf of this sheaf of divisorial algebras, which is locally generated by elements of this form. Anyway, if this is confusing, or if this is the first time you hear it, you can just drop the whole part and assume that the divisor class group is free. Free abelian, and then K is isomorphic to CL of X, in what follows, and that's okay. Okay, so now here are the two objects under the same assumption as before on X and on the divisor class group. You can define two objects, and the two of them are important for us. I cannot skip any of them. So first of all, the first one is the Cox sheaf, which is this quotient, or if you want to just think about the simplification, just take S whenever the divisor class group is free. And the second one is a ring or algebra of global sections of the Cox sheaf. Okay? So there is some notation after, it's a kind of definition after the Hu-and-Kiel paper. Whenever R of X is finitely generated over a finitely generated algebra over the complex numbers, then you call X to be a Moritzring space. The original definition of Moritzring space is geometric, but it is equivalent to this one due to their result. Okay, so the problem that I want to address is the following. There are, when you start studying Moritzring spaces, the easiest one are toric varieties. So these are equivariant compactification of a maximal torus. Torus is a C star to the n. Well, n is the dimension of the variety in this case. Okay. Why they are a kind of basic bricks of the theory of Cox rings, because the Cox ring is a polynomial ring if and only if the variety is toric in the projective context. So it's not only finitely generated, but also you have no relations. Then you have a subvariety of a toric variety, and you would like to know something about the Cox ring. So these Cox rings, they are kind of, well, if you see for the first time, it's not easy to understand what is going on here, but a kind of basic example is when you start with the projective space, and then in that case, if the projective space has dimension n, then the Cox ring is the polynomial ring in n+1 variables. Then by the construction that we gave of this, it is, so this is k graded, and the Cox ring, the Cox sheaf is CL graded. Then the grading in this example is the usual one on the polynomial ring in the n+1 variables. All the variables, they have degree 1. Okay. So what about this Cox ring of the embedded variety? I'm going to give a theorem, to give a statement about this, and mostly we applied to the following. So take smooth toric Fano variety of dimension n greater than or equal than 4. The reason of the dimension is because of Lefschetz hyperplane theorem. Pick a rank 2 and take X to be a general anti-canonical hypersurface. So this is Calabi-Yau. Then X is a Moritzring space. And the Cox ring is a complete intersection, and it's given in the following table. I'm going to show it's a little bit small, but I think it's, I hope it is possible to read from. Sorry? Wait, n is greater than or equal than 4. Yeah, the reason for this, the problem with the cubic surface is that I don't have an isomorphism between the divisor class group. I want this isomorphism by Lefschetz. So that is the reason of the assumption. So now let me take f equal to 0 to be a defining equation for x in Cox coordinates. I'm going to be a little bit more precise about what this means in a while. But basically, if you think about the projective space, you can think about equations of subvarieties of the projective space given by homogeneous polynomials. It's exactly the same thing. Okay, then there are 3 possibilities for the Cox ring. In the first case, basically the notation means that the irrelevant ideal of the ambient toric variety does not have components of codimension 2. So it has 2 irreducible components. They are 2 linear spaces, or both of them, they have codimension 3 or more. In that case, the Cox ring is a hypersurface and is given by the same F. So second case, we have one 2-dimensional component, so one codimension 2 component of the irrelevant locus, and this is generated by the vanishing of the first two variables in this case, and the two variables, they have the same degree. So if you want to translate, this simply means that your toric variety admits a morphism onto P1. In this case, the Cox ring is a complete intersection with two equations, and the two equations, they come from the shape of F. So it is easy to see that when you write down F, this is written in the following ways: F0 T1 minus F1 T2, and in this Calabi-Yau case, this is unique, but it's not really important. You can have more than one way to write down this with the F0 and F1, but anyway, they are going to produce isomorphic Cox ring. This is not very important. So from this way to write F, you can extract the two equations and also the new generator, which is S, that is F1 over minus F1 over T1 or minus F0 over T2. And the third case, you have that the irrelevant is still of codimension 2, but the degree of the two variables, in this case, they are the variables Tn plus 1 and Tn plus 2, these two. They are different. This is a kind of blow up of a weighting projective space, and the Cox ring has three relations, and you have two new variables, this S1 and S2. So in what follow, I want to give you an idea of the proof of this result, or of this type of results. Okay. Okay, so first of all, let me recall you something. Whenever the variety is Q factorial, so we are in the smooth case, so this is completely okay, the Cox sheaf is locally of finite type. And you can produce the following construction. So on one side, you have the Cox sheaf, and you can take the relative spectrum of the Cox sheaf. So, I mean, you cover X with a fine open subset, and then you do over each one of them the usual spectrum. And on the other end, you have the spectrum of the Cox ring. And it is possible to prove that this embeds as an open subset into this one, that X hat is an open subset of X bar. Moreover, it has a complement which is of codimension at least 2. This is a kind of, this is what is called, the complement is what is called the irrelevant locus. Okay, I want to stress the fact that the whole construction stays the same even if the Cox ring is not finitely generated. So even if this is a non-Noetherian scheme, then the same, you have this construction, and this embeds into this one, and the complement is of codimension 2. This is a kind of fundamental in our construction. Okay. So then the quotient construction, which is in the case of projective space, this is the projective space, this is C to the n plus 1, and this is C to the n plus 1 minus the 0. And this quotient construction is given by this quasi-torus, that is the spectrum of the group algebra over the divisor class group. Basically, the grading of the Cox sheaf is given the action of this quasi-torus. Okay. Now, due to this construction, I mean, the Cox ring is by definition a ring of a global section of X bar, by the definition of X bar. And well, it is possible to show that X is a normal scheme. So this is also a ring of global sections of X hat. This is quite important because this normality criterion is used, I mean, the regular functions, they extend. Okay, this is one of the ingredients. It's quite central in the theory. And now we are going to introduce a second one and then a third one. Okay, so let's see, projective variety with finitely generated Cox ring. I'm assuming Z is to be smooth. When we do the construction of the Cox ring, we need this subgroup K of the group of Weyl divisor projecting on the divisor class group. This I'm calling K of Z. And I'm assuming the subvariety X of Z not to be contained in the support of any element of K of Z. If you want to take the example of toric, you take Z to be toric, then this is a group generated by prime invariant divisor, and you just have to ask that X is intersecting the big torus. That's enough. Then there is a commutative diagram. On the right-hand side, we have the characteristic space of the Cox construction that I showed to you. This is Z hat that is a relative spectrum of the Cox ring projective on Z. And on the left-hand side, we have the following. We have X contained in Z and the pre-image of X via this map. Okay? I put the name X hat because it is X hat. That's, yeah, it was, okay. So, but in principle, the definition is this one. Okay. Now, this is basically a result which is in a paper by Jürgenhausen, and we rewrote in this book on Cox rings. So assume, so right here I put no hypothesis, but now I'm assuming that the pullback map from the divisor class group of Z to the divisor class group of X to be an isomorphism. Okay. So assume this, for example, this is automatic by Lefschetz whenever X is ample. Then there is an isomorphism of CA graded of X algebras. So this is the Cox sheaf, and this is the push forward of the sheaf of regular functions on X hat. Okay. So in particular, as a consequence of this, this map that I showed before is a characteristic space, and X hat is normal. Okay. Okay, so this means, this is our second ingredient, this means that we don't have the Cox ring, but we have the Cox sheaf. And we have the characteristic space. So now let us put some notation. We have this Z bar. Whenever we have this Z hat, this is the characteristic space. It embeds in the spectrum of the Cox ring. This is a Z bar. And then we take X tilde to be the closure of X hat into Z bar. The reason for this X tilde is that this is, in general, this is not X bar. It's not the spectrum of the Cox ring. Okay. Then we have inclusions. I don't know which way to put this. We have this X hat. We put this X hat into X1 tilde and then into X tilde. I apologize for the notation, okay? So what I want to stress is that going from X hat to X1 tilde is not adding divisors. And going from X1 tilde to X tilde is adding all the divisors. So I take this complement. In this complement, it could be the case that there are divisors. All of them I put outside this X1. I just throw them away and I keep this X1 tilde. Okay? So X hat is big into X1 tilde, and then we have this X tilde, adding the divisors which are outside. Okay, this is a kind of fundamental. So then we have this theorem. Assume that this is an isomorphism and that X1 tilde is normal. Then this assumption is fundamental. Okay. Then we describe a basis of this ideal. Let me remind you that this is consists of divisors in X tilde, because I'm for moving from x hat to x1 tilde, I'm just removing divisors from x tilde, okay? Then the Cox ring is the intersection of this localization. So this is a ring of regular functions of x tilde into this affine ambient, which is a z bar. And these are localizations with respect to this element, and this is an intersection of this. So in particular, if x1 tilde coincides with x tilde, or equivalently, if x hat is as big inside x tilde, there are no divisors between the two, then we have something which was already known both in this paper and in a joint work with Michele Artebani, and then we reformulated more precisely here. The Cox ring is given just by this quotient. Yes. The grading, so this is homogeneous because there is this isomorphism. So this is, let me just move to here, maybe. Then, for example, this variable S, which is an element in the localization, takes the degree of F1 minus the degree of T1. Because when you move to the localization by a homogeneous element, maybe I haven't written, sorry, homogeneous spaces. You are completely right, yeah. Sorry. Okay, but this is taking the degree from them. Then, okay, the proof of this is very easy, so I'm going to show. The first equality is the definition of Cox ring. Then the second one is because of the proposition that I gave you. So the Cox sheaf is the push forward. So we have the Cox sheaf. Okay. Then, the third equality, there is nothing to say. The fourth equality is because of the normality assumption on x1 tilde. That is where we are using this assumption. Then we have this x1 tilde. This is complement of x tilde with respect to this, which is generated by homogeneous. And then this complement you can write down as a union of this. This is a kind of standard notation. We are removing one of them. And if you want regular function on this union, then they are intersection of regular function on each one of them, and then you have the results eventually. So this is quite straightforward. So basically now we have a description of the Cox ring of the embedded variety as an intersection of localization, okay, which is a kind of natural bind. Okay, now what to do with this? The point is trying to guess new generators, knowing that this is the structure. So we have two propositions. Let me show them to you. So first one, R is finitely generated normal. This should be CL of X graded algebra. These are homogeneous elements of R. They are exactly the same as before. And R prime is a K-graded algebra, which is in between R and the intersection of localization. This is what, yeah. Then we want to know when we have an equality here, so that we have the Cox ring. And there are two equivalent conditions. So if you think about what I told you before, let me go back for a second. There was this in particular, no? Whenever there are no divisors, I mean whenever x1 tilde coincides with x tilde, then you have the Cox ring. So following the same idea, we can show that the only thing that we have to check for guaranteeing that R prime is equal to this intersection of localization is that the codimension of this locus, so the vanishing locus of these elements is at least 2 inside spec of R prime. So this is a kind of criterion that we can use for saying, okay, we have the Cox ring of the embedded variety. On the other hand, it is a kind of difficult to check this because it is difficult to write down in general spec of R prime. I mean, you start with R, you add new elements, which are fractions that can be written with several distinct denominators. And after adding these fractions, you need to produce relations, and then it could be a mess. So sometimes it is enough to produce just a subset of the relations, and then you are able to prove that this holds, and then you know that your set is generating the whole Cox ring. Okay. Another observation is where to look for new generators, so in which way you can form this R prime. Well, we are looking for fractions of this form, because if you are in a localization by M1, you have a fraction of this type, which can be written as a fraction of another type, some f over M1 to the n, which can be written as a g over M2 to the m. Then, if you think a little bit about this, this just implies that f is in the saturation of M1 to the n with respect to M2. And since this can be written in all possible ways, then it must belong to this saturation, and you can write down a computer program for producing these elements. So from one end, you have an algorithm for doing calculations, and on the other end, there is also something which is a little bit theoretical, which allowed us to give the statement that I showed to you. So then we decide to apply, how much time? 11, thank you. To apply this machinery to the following situation. So let us say that we have a smooth projective toric variety whose Cox ring, this is, as I told you, is a polynomial ring, which has just one component in codimension 2. We are still trying to classify toric varieties admitting this condition. So it's not difficult to say something about the polytope or the fun, but in general, not so easy. Okay, anyway. Then you take X, which is a normal ample hypersurface. Whose defining for polynomial in Cox coordinates is f. This means that f is a defining polynomial simply for x hat, as I defined it before. Then it is easy to see that f is written in the following way, where you have a kind of Veronese in this T1, T2, and then you have coefficients. So we could prove that if this locus into C to the R as codimension d plus 3, I mean, if this is a kind of complete intersection because there are d plus 3 of these polynomials, then the Cox ring is exactly this one. In this case, you work with the intersection of localization with respect to T1 and T2. So the elements that are appearing here, it's not difficult to see that each one of the new variables S can be written as a fraction of a homogeneous element divided by a power of T1 or a homogeneous element divided by a power of T2. I'm not going to explain the proof of this, not very complicated, but the ingredient I gave to you. So now there is one case where it is very easy to consider this when you have picker rank 2, then in that case smooth toric varieties of picker rank 2, they are very easy to classify. And basically, you can have no component of codimension 2 in the relevant, or just one, when the dimension of the toric variety is big enough. We are bigger than or equal than 4, so it's okay. So these are the two possibilities. In Pika rank 2, Z is smooth toric projective. We take a general ample hypersurface. Then there are two possibilities. Either the grading of the toric variety is this one, or it is this one. And the relevant in this case is given by the first two. The codimension 2 component is given by the first two variables or by the last two. So applying the previous result, we could show that here we have the Cox ring whenever the degree of our hypersurface. So in order for the hypersurface to be ample, it has to belong to the positive quadrant. So A and B, they have to be positive. So B here can be whatever you want, but A has to stay in between bigger than 0 and at most this number, which depends on how many AK are equal to 0. And in the second case, the bound is on B. So we have different bound on A on B for having the Cox ring. So this is the situation. Then, if you think about this, you immediately get as a corollary the theorem that I presented at the beginning, because in the grading matrices of this toric Fano, there were a lot of zeros here. And this is important. Let me show the original. So as you can see, there are a lot of zeros here. And just 1 minus 1. So that is basically, it comes immediately after the statement that I showed to you. Okay. So then, what can we say more? After doing this, another thing that we started observing was what happens if we go beyond this bound here. So if we move outside, then it seems that the number of generators of the Cox ring, at least computationally, explodes. Unfortunately, we are not able to use this criterion for proving non-finite generation. This is, we could use only for proving the finite generation, but we found a paper of Otten where he studies something similar, and here there are two beautiful results. So X is in P1 times Pn minus 1, general hypersurface of degree AB, and as I told you before, when you have two variables of the same degree, there is no condition on B, but we have this condition of A. A, in this case, must be less than or equal than n minus 1. In this case, we have the Cox ring, and it is a complete intersection. Outside this condition, if B is equal to 1, we are able to prove that this is a scroll. So Cox ring is it's a toric. It's just with another, so it's a little bit hidden here, but after change of coordinates, you can recognize the scroll. And if B is greater than or equal than 2, then no one of them is a Morrison space. And his result consists in proving that these three cones coincide and that they are open on one side. The argument is by the generation to a singular variety, which is linearly equivalent to X, and the minimal resolution of this is a P n minus 2 bundle over an elliptic curve, and this is very well known, and you can do all the calculations and prove that at the boundary of the big cone, in that case is also, I mean, of the effective cone, there is this class which is never effective. So this is not a Morrison space, but the argument for proving this is non-algebraic, is a geometric one. We couldn't even get closer. We just see that the number of generators is exploding. So then we decide to stay with Calabi-Yau so just for a very little time. Stay with Calabi-Yau inside toric funnel, but also there is nothing to do because in the same paper there is this other one, which maybe is coming from an example by Ogiso. Anyway, you have P1 cross P1 cross P2, then you take X, which is Calabi-Yau in the anti-canonical of degree 2, 2, 3. So since you have these two, you have two birational involution. They are coming from the degree 2 coverings from X into P1 cross P2. It is not difficult to write down the matrix of the action of each of these birational involution on the picker group. They are small birational involution. If you write down the matrices, then you immediately convince yourself that the composition of the two is an automorphism in codimension 1 of infinite order. So this cannot be a monitoring space as well. Yeah, then this is more or less the context of our result, and then this is just the bibliography of what I told you. I mean, are you talking about this? I mean, the relations are here. You want them geometrically? We haven't thought about this. I guess there should be some I mean, a priori, having the relation, I can describe all the cones, the automorphisms group. We haven't done this yet, but we can describe these things. But knowing if the relations, they come from some special locus on the funnel, they for sure they come from some special locus in the equation itself, but I don't know if they are encoded by some tangent space to something or something like this. No, this I don't know. I don't see it. Because everything is very algebraic, this intersection of localization and it works the same. So I think that there could be several applications because we moved to toric because we wanted to just to be sure to do something correct, to do calculation with the computer, and then in that case you start with the polynomial ring equations, but then I think you can in principle move to. In this one, I don't remember how I formulated smooth projective with finitely generated.
Further questions? Okay, if not, let's thank them. We resume in 8 minutes.
Gracias. ¿Saco eso? ¿Y tenía algo acá o no? Sí, tengo algo acá.
Gracias. Vamos começar às 40 ou às 40? Ok.
Okay. So 3:40, it's time for another call. And the speaker now is Olivier Martin, who will digress about the irrationality and the Gauss map, or irrationality of the Gauss.
No, and the Gauss map. All right, well, I'd like to start by thanking the organizer for the opportunity to speak and organize such a nice session. It's been really nice so far. All right, so what I want to talk about is a Beyond variety. So throughout, I'm going to have a Beyond variety over C. C is going to denote typically a curve inside of my Beyond variety, and I'm going to write pi for the normalization of that curve. And since I want to talk about curves on a Beyond variety, well, let me first recall, before I get any further, what the gonality of a curve is. This has nothing to do with curves on a Beyond variety specifically, but the gonality of a curve is the minimum of the degree of phi, where phi is a non-constant, or if you want a dominant rational map from C to P1. Another way of saying this is the minimum of D, such that the normalization of D has a G1D, which is a line bundle of degree D with at least two sections. Then you can use these two sections to get you a rational map to P1. And I want to make the following definition. Basically, when you have a curve on a Beyond variety, you can always translate that curve. So I want to get rid of those translations. And so I'm going to call so a k-gonal curve, or maybe a d-gonal curve, C in my Beyond variety is normalized if so this is going to so if C tilde has a G1D delta such that given x1 plus xd in delta, when you do pi of x1 plus pi of xd, this is equal to 0 in my abelian variety. Okay, so just to avoid any confusion, I'm using two different notions of sum. Here, I mean a zero divisor of degree d, right? A formal sum of d different points on my curve. And here, those pi of xi's, those are points on my abelian variety, and I sum them up using the group operation inside of my abelian variety. Okay, so just a few remarks about this definition. So every diagonal curve, or every curve really, inside of my abelian variety can be translated to a normalized curve. And really, most of the situation that we're dealing with, I'm going to be dealing with curves of relatively low gonality on abelian varieties of large dimension. So they're going to have only one linear system of degree d, so they're going to be uniquely diagonal. And so there's actually going to be only one translation, but not that really matters that much. And one place in which this shows up, for instance, if you have a curve inside of an abelian variety which is hyperelliptic, then C is normalized if and only if, when you quotient by plus or minus, you get a curve inside of A plus or minus 1, if only if that curve is rational. Okay, so one of the reasons why I'm introducing this notion of normalized, as I said, is to rule out translations. And you get, for instance, the following lemma. This is a really well-known, this is not anything new, but this is a really well-known result about hyperelliptic curves on abelian varieties. So statements that normalized hyperelliptic curves on abelian varieties are rigid. And so I'll give you, so basically what I'm saying here is if you have a hyperelliptic curve inside of an abelian variety and you want to deform it, the only way that you can deform it is through translations. And let me give you a sketch of a proof. The proof is really quite easy. And the reason why I want to sketch the proof is because I'm going to generalize the statement, and I'm not going to give you the proof of the generalization, and the proof is basically the same but more complicated. This proof is really, really easy. Okay, so what's the situation? So suppose not. So you have your abelian variety, you have your hyperelliptic curve, and you can deform it in, let's say, one parameter family. Right, so you get your A, and you get a surface S inside of A. And what you can do is you can look at the map to A mod plus or minus. So downstairs, you're getting this A mod plus or minus, which is a singular variety of some dimension. And downstairs, because these curves were normalized hyperelliptic, they're now going to be rational. And now we have a family of rational curves. One parameter family of rational curves. Okay, but let me call this S mod plus or minus. And just to make things clearer, you don't really need to do this, but I just want to avoid any kind of confusion. So I'm going to take desingularizations of these two things. And so what happens in this situation is that your S mod plus or minus, this desingularization, is uniruled. And since it's uniruled, it doesn't have any holomorphic forms. It doesn't have any canonical forms. right? So if you look at the composition, H naught of A mod plus or minus desingularization, omega 2, and you restrict it, right? This is a restriction to H naught of S mod plus or minus desingularize omega 2, this map is 0. Right, this map is 0 because this group is 0. Okay, and then it's really just a local computation. It's easy to see that that's complete nonsense, because if I give you a point upstairs, general point upstairs, you have some tangent space. You have so many 2 forms on A that you can certainly find a 2 form that doesn't restrict to 0 on that tangent space, right? The 2 forms on A are they're just constant form, right? So the tangent bundle is trivial, so your wedge 2 of the cotangent is also trivial, so you can find plenty of forms. You can find a form that doesn't restrict to 0 on that tangent space. But then the point is that the 2 forms are invariant under the plus or minus 1, because the 1 forms are anti-invariant. And so all of the 2 forms you have upstairs descend to 2 forms downstairs. And since you found a form upstairs that restricted to something non-trivial here, when you descend that form downstairs, it's going to descend to something non-trivial there. So it's a local analysis that tells you that this doesn't work. So local computation says this is nonsense. This is wrong. Okay, so this completes the proof. So this is a little I hand waved a little bit, but this is correct. Any questions about this argument? Okay, so yeah, so I mean, you need a little bit of mixed Hodge theory, maybe, to say that. So if you have a form down here, it's really going to give you a holomorphic form. Yes, you're extending it, but basically it's a local thing, right? So to check that a form, if you have a form that doesn't vanish locally at a point, then that has nothing to do with the extension, right? I'm looking at smooth points, for instance. It's completely fine to do everything on the smooth locus. Okay, so the point of this talk is to ask what happens. So I mean, I came into this problem because I was trying to understand what are the simplest curves that you can have on a general abelian variety, and then I noticed that there was something fishy going on, and so I was led to this theorem, which is a generalization of unfortunately the thing that I just erased. Maybe the theorem that I just proved that's behind. So the theorem is the following. So I'm asking what happens if you take not hyperelliptic curves, but the next best thing to hyperelliptic curves. So the next things are trigonal curves that have a degree tree map to P1. And the theorem is the following. They're not necessarily rigid. At least I can't prove that they're rigid. I think they're rigid. I can't prove that they're rigid, but I can prove that they're almost rigid. They can move at most in a 1-parameter family. So normalized trigonal curves. Let me call this theorem A. On abelian varieties move in at most 1-parameter families. Okay, so a few remarks about this. On normalized trigonal on abelian varieties of dimension, sorry about that, of dimension greater or equal to 3. Okay, so a few remarks about this statement. So the first remark is that if A has dimension greater or equal to 4 and is general, then it does not contain trigonal curves. So this is a theorem of Alzezzi and Pirola. from, I think, 92. Okay, so what's strong about this result is not, this doesn't really say anything particularly interesting about general abelian varieties. This is really, the strength is that it holds for every abelian variety, which is, those types of statements are a lot harder to get. The second statement, the second remark, is that the dimension assumption is necessary. And the reason for that, it's quite easy to find an example. So if I have AL, a 1,4 polarized abelian surface, so what it means to say that it's 1,4 polarized is that when I look at the complete linear system corresponding to that line bundle, this is going to give me a net, so a two-dimensional linear system of genus 4 curves. Genus 4 curves are either hyperelliptic or trigonal, but the hyperelliptics are rigid, and so for sure these have to be trigonal. So you get a two-parameter family of trigonal curves, and okay, you might protest, okay, well they're not normalized, but you can just normalize, move them all so that they're normalized, and so now you have a two-parameter family of normalized trigonal curves. So you can do better than a one-parameter. And on the other hand, this is sharp for abelian treefolds. So Pirola produces abelian treefolds containing one-parameter family of normalized trigonal curves. I mean, really, this is just a statement. I mean, if you can produce a one-parameter family of a non-isotrivial one-parameter family of curves, again, you can move them all so that they become normalized, and it gives you a one-parameter family of normalized. Yes? Yes, you're right. Okay, you're absolutely right. Non-degenerate. So, sorry about that. That means forget about your example, and then so remove the counterexamples, and the statement is correct. Yeah. Sorry? Yeah, exactly. Sorry about that. So non-degenerate means that the curve spans the abelian variety. So if you look at the curve and you look at the summation of the points on the curve, eventually you're going to get the entire abelian variety. So it's a very natural assumption to put, because again, otherwise you're looking at a curve in an abelian variety, but really your curve sits in a smaller abelian variety. So any type of statement about the curve is not really going to see the geometry of the whole abelian variety. It's only going to see the geometry of the curve, the abelian variety that it spans. And the last statement is that you get similar statements for all gonalities. So what do I mean by that? Well, what I mean by that is if you put some really mild assumptions, it's really easy to show that the exact same statement, except you don't show that they didn't move in at most one parameter family, but you show the biggest family is the gonality minus 1. At the moment, I need some mild assumptions, but it's probably just a matter of a little bit of linear algebra to get rid of those assumptions. So presumably this is true for all gonalities, but I'm not quite ready to state it, so I'm going to keep it this way. Yes. No, I mean, well, if it were isotrivial, if you have an isotrivial family of curves in an abelian variety, they're translates of one another, right? So then they're not normalized, right? I mean, okay, that's a little bit, but if they're, okay, if they're uniquely trigonal, so in the cases that are interesting, then if you have an isotrivial family, they're not normalized. Okay, so let me state the second. So this was the first term, and then the second term is saying something about what happens about when you have a one-parameter family. So what I was saying is I'm hoping that for large enough abelian varieties, you just don't have any one-parameter family. So they're rigid, just like hyperelliptic curves were rigid. So I expect, for instance, trigonal curves maybe are rigid in abelian fourfolds. So the Viola counterexample tells me that they're not rigid in abelian threefolds, but it could very well be that starting from dimension 4, they're rigid. And so let me tell you what families of trigonal curves look like. So if you have a family of trigonal curves, you can say a lot about the geometry of the surface that's covered by these trigonal curves. And this is the content of theorem B. I apologize, I'm going to write a precise statement. It's going to be ugly because they're families, and it's just going to be a bit of a pain to write down the precise statement. Then I'm going to draw an even more precise picture that's going to make everything very clear. So I just felt the obligation to write some math and not just draw pictures. So A is going to be an abelian variety of dimension greater or equal to 3. I'm going to look at a family of curves. And I want to formalize the fact that it's a family of trigonal curves. And so I'm going to pick a map that's degree 3 onto its image T over the same base. And this has rational fibers. Right, so this is basically a family of trigonal curves, and I'm kind of registering the fact that the trigonal linear system, I'm kind of gluing the trigonal linear systems together. And I'm going to look at a map from C into my abelian variety. And I'm going to require that this map is birational, so restriction to fibers of C to B is birational on its image. Okay, so this setup is basically a family of trigonal curves inside of my abelian variety, right? Because when you look at the fibers, the image is birational into its image. So it's, the fibers are basically curves inside of this abelian variety, except maybe I'm doing a normalization or something like that. And I haven't put this normalized assumption yet, so that's the next step. I'm going to put this, and I require that given T and T generic, and if phi inverse of T is equal to x1, x2, x3, I require that f of x1 plus f of x2 plus f of x3 is equal to 0. Okay, so this, basically all of this setup is just a family, a one-parameter family of normalized trigonal curves inside of my abelian variety. This is the thing that I was saying was a little bit painful, but now I can write down the statement. I apologize for writing a theorem that takes half a board to write the setup, but and so the claim is that then for T and T generic. And so let me do one more thing. Let S be f of C. So this C is a family of trigonal curve. The S is basically the surface in the abelian variety that's covered by this deformation of trigonal curves. So then for T and T generic, write T inverse of T is equal to x1, x2, x3, like I had before. And then I have the following equality of tangent spaces. The tangent space to S at f of x1 is equal to the tangent space to S at f of x2 is equal to the tangent space to S at f of x3. Okay, so here comes the picture. I have my abelian variety. I have a family of trigonal curves inside of my abelian variety. I pick a generic point in T. So basically, what that means is I pick a generic one of these trigonal curves, and I pick a generic divisor of degree 3 that's in its trigonal linear system. So I pick 3 points like this that map to the same thing by the map to P1. Those are my x1, x2, x3. What I'm saying is that I have the tangent spaces to the surface at these 3 points, and the 3 tangent spaces are the same. And this is very strange. I mean, this is quite odd, and certainly not something that you would expect to happen from a random surface inside of an abelian variety. And can I lower the board, or is it have people absorb the statement a little bit, or should I let us? Any questions about this statement? Okay. So maybe before I change, I'll just say a word about the proof. So I'm not really going to prove it, of course, but the proof is not hard at all. So just the word about the proof is that, so sketch of proof. So this one parameter family of trigonal curves, it gives rise to a uniruled surface in what I'm going to call symmetry 0 of A. So this is contained in symmetry of A, and it is the triples of things that sum up to 0. So this is okay. This is like absolutely sinful notation, but so the triples of points that sum up to 0. So the pluses on the left are not the same as the pluses on the right. So the pluses, maybe I should just write. Okay, so this is a triple of points such that when you add them up inside of the abelian variety, they give you 0. Okay, so this correspondence is very much the same thing that I had at the beginning with hyperelliptic curves, except in that case I was looking at sim2 of A, and sim2 0 of A was exactly the quotient by plus or minus 1. So I have exactly the same situation. So I have this family of every trigonal curve gives me a rational curve in symmetry 0 of A by basically looking at the fibers of the map to P1. And so a trigonal curve gives me a rational curve, so a family of trigonal curves gives me a family of rational curves. And now this uniruled surface, I do the same game. I have all these two forms in symmetry 0 of A. I can restrict them, and all of these restrictions have to be 0. And then it's a matter of unpacking the linear algebra, and it's not at first sight completely obvious that you get a statement that's as clean as what you get in the end, but you do get that statement about the quality of the tangent spaces. Okay, so let me spell out a few consequences and get to the title of the talk. Okay, so before I spell out the first consequence, let me just recall for you that if you have a surface inside of an abelian variety, the Gauss map of S is the following map. So I'll denote it G. It goes from S into the Grassmannian of planes inside of the tangent space to A at 0. And it's defined in the following way. So you take a point to a point, you associate the tangent space to your surface at that point. Right? This is a rational map. It's defined outside. It's defined on the smooth locus of your surface. And so a consequence of what I just told you is that if you have a surface inside of an abelian variety, the dimension of A is greater or equal to 3, and S is covered by normalized trigonal curves, then the Gauss image of S is uniruled. And in particular, the Gauss map is non-generically finite on its image. Okay, and for me, that's a very strange statement. My expectation is the Gauss map, if you look at a surface in a large dimensional Beyond variety, you have a lot of room there to, you're asking that basically the tangent space of your surface agrees at a bunch of different points, right? This is a very strange, strange statement. My expectation is that if you look at a surface in a large, whatever surface in a large enough dimensional Beyond variety, the Gauss image, the Gauss map should always be generically finite, birational on its image. Such a statement. And well, I mean, so basically on each of these trigonal curves, when you restrict the Gauss map to these trigonal curves, and you look at a triple of points in the linear system, the tangent spaces agree, and so you get 3 points that map to the same. It doesn't quite mean that it's 3 to 1. It almost means that it's 3 to 1. It doesn't quite mean that it's 3 to 1 because you could have a point could lie in several trigonal curves, right? If you knew that really this family of trigonal curves covered birationally your surface, then it would just tell you that it's 3 to 1. Just by, no, sorry, not birational. Absolutely right. It is generically finite on its image. That's a well-known statement, well-known result about non-degenerate, geometrically non-degenerate subvarieties. Sorry? Yeah, it will be generically finite. It won't be birational on its image. Sorry about that. And so that's the first statement I wanted to give. The second statement is the same lines. So it says that if S inside of A, same setup, the dimension of A is greater or equal to 3. So if phi from S to, let's say P2, but really it would work in much bigger generality, if it's generically finite of degree, if it's dominant of degree 3, then the Gauss map of S factors through phi. Right, so in particular in that case, you would get that the Gauss image is rational. And it's a very similar statement. You see, in that case, this map of degree 3 from S to P2 gives you a ton of rational curves. Sorry, it gives you a ton of trigonal curves, because you can take any line, for instance, in P2, you can pull it back, and you get a trigonal curve. Okay, so this is something that I've been quite interested in. So there's a notion that people have been looking at, which is called the degree of irrationality of a variety. So the degree of irrationality of a variety X is denoted Ir of X, and it's the minimum of the degree of phi, where phi is a dominant rational map from X to projective space. Okay, and so this basically tells you that if you have a surface inside of an abelian variety of dimension at least 3 that has degree of irrationality 3, its Gauss map is really special. It's really strange. And you get some consequences out of that. So I have 8 minutes, so maybe I'll try to finish with a nice little theorem that's also going to give you a bit of a puzzle if you're interested in these questions. So the last corollary I want to discuss is the following. If C is a smooth genus tree curve, then the degree of irrationality of sim2 of C is greater or equal to 4. Right, so it's a smooth genus tree curve. If you look at sim2 of C, it's a genus tree theta divisor, divisor inside of the Jacobian. And I'm saying there's no degree tree map to projective space, to P2. And it's easy to show that there's no degree 2 maps to P2 because then you'd get an involution. So in this game, basically, showing that something is not rational, well, that can be very, very hard. But in the type of situation where you look at subvarieties of abelian varieties, they have form, so they're not rational. And showing that they're not double covered is also relatively easy. And then going from 2 to 3 becomes basically hopeless, unless you get these types of, you really need to have some new ideas to pass from 2 to 3. Okay, so this is interesting because it's quite hard to find lower bounds, significant lower bounds on this degree of irrationality, and so any type of new technique that you get to show these new lower bounds, I think is a good thing. And so let me give you the proof. So it breaks into 2 cases. So if C is hyperelliptic, it breaks into 2 cases, but in both cases, basically what you need to do is, if the degree of irrationality was 3 because of the previous corollary, the Gauss map would factor through this degree tree map. So basically, you just need to show that the Gauss map of this thing doesn't factor through a degree tree map. Right? So the claim is the Gauss map of sim2 of C inside of the Jacobian of C does not factor through degree tree map. And the first case is easy. If C is hyperelliptic, the Gauss map of sim2 of C to, in this case it's P2, this agrees with sim2 of the canonical map. Right, so the canonical map of a hyperelliptic curve is the double cover of a rational curve. And so this is, in this case, is the degree 4 map. Right, and the degree 4 map doesn't factor through a degree 3 map because, well, 3 doesn't divide 4. So just numerically, you see very easily that it can't possibly factor. In the case of a non-hyperelliptic curve, it's also easy because you can write down what the Gauss map of the theta divisor is very explicitly. So if C is not hyperelliptic, then the Gauss map of the theta divisor looks like the following. So it's, again, sim2 to P2. And if you have a non-hyperelliptic genus tree curve, the canonical map is an embedding, and it's an embedding as a quartic curve in P2. Right? So this C is a quartic curve in P2. And you take 2 points on this quartic curve, and you associate to it the line that they span. Right? So the construction is really the following. You have P2, you have your quartic curve, and given 2 points, you're going to draw a line that they span. It's a line in P2, so it gives you an element of the dual. And this is the degree 6 map. So numerically, there's no 3 divides 6, so it could potentially factor. There's no numerical obstruction to it factoring, but there's a monodromy obstruction that's very well known. The monodromy of if you fix a line and you get 6 points over it, and then it gives you as you move the line around, it gives you a representation into a symmetric group on 6 elements, and the monodromy group in that case is the full symmetric group. So this is a really well-known statement. So there's it couldn't possibly factor, because if it factored, it would tell you that the pairs of points split up in some way that violates monodromy. So I don't want to talk too much about this, but this is the proof. Okay, and part of the puzzle I wanted to ask you is that certainly if C is not hyperelliptic, you don't expect that you would have a degree 4 map at all. You don't expect that you would have a degree 5 map at all. And I would very much expect that the Gauss map of the theta divisor is the lowest degree map to P2. But showing that you don't have any degree 4 maps or 5 maps, I've tried, and it's, I mean, for me it was hard. I haven't been able to do it. And maybe just let me say a word about the context of this statement to put it in perspective. So the context is that Bastianelli proved in 2012 that Sim2, the degree of irrationality, so let's say C is a hyperelliptic curve. Then he proves that the degree of irrationality of Sim2 of C is equal to 4 if the genus of C is greater or equal to 4. Right, so, and this is, I mean, this is significantly easier than the genus tree case because you get a lot of, in all of these things you use that you have a lot of forms and you use some positivity properties. And so in these cases, you get a lot more positivity than the genus tree case. The genus tree case is harder, and as you decrease the genus, it gets harder and harder. The genus 2 case is still wide open. So if C has genus 2, Sim2 of C is an abelian surface. It's a Jacobian, genus 2 Jacobian. It's not known what the degree of irrationality of a genus 2 Jacobian is. And so let me just leave you with, I still have a minute or 2 minutes, right? Wonderful, that's plenty. So just I'll just leave you with a few questions that are related to these things. So one was, I won't write it down because I'm out of time, but one is, are trigonal curves rigid on large dimensional abelian varieties? So it looks, from what I'm saying, you know, I very much believe that they're rigid, and so that's one question. Another is, are there surfaces in abelian varieties of dimension either greater or equal to 4 or greater, really greater than, you know, really big, with degree of irrationality, or even greater or equal to 3, with degree of irrationality equal to 3. And here I certainly need to put non-degenerate as well, because certainly there's abelian surfaces, there are abelian surfaces with degree of irrationality 3. So again, these, and you know, both of these statements about the rigidity of trigonal curves and the statement about the degree of irrationality, they kind of boil down to this question. So are there surfaces in abelian varieties of large dimension whose Gauss image, no, I'm really out of time, whose Gauss images are uniruled / rational. And of course, all of this, you know, I'm talking about surfaces here, but you could try to do things in any dimension. You know, all these statements should have analogs. Done.
Thank you very much, Olivier. Nice talk. Questions?
Yes. Yeah. Yeah. Well, the theta divisor is Sim2 of C. Right. So it's at least 4. And if it's hyperelliptic, then you have a degree 4 map, which is Sim2 of the hyperelliptic map. And so the one that's left over is if it's not hyperelliptic. So I think that degree 6 map is it. I think that's the lowest degree map. And sorry? That would be my guess, that it has degree of irrationality 6, but that's open.
And you also said that one known
Yeah. Yeah. So basically, if you give me take any surface that's not rational, and that's not like an Henry case or something, and take any surface of general type, and the degree of irrationality is probably not known, unless it's, you know, a double cover or something silly like that. So the cases in which it's known are, We have very, very few like cases in which we can even bound, cases in which we can compute. There's like really, really few.
Questions? So we resume in 8 minutes, but let's thank Olivier for
Merci. Well, I don't. It's usually I'm sweaty after a talk, but this is I can't wait to put on my jacket. Thank you.
¿Y esto lo pongo en el bolsillo o algo así? Ah, perfecto. Genial. Ya, muchas gracias. ¿Bajamos el telón o todavía no? Sí. Así que por eso esos, los dibujos. Sí. Un minuto.
Okay, so it's 4:30 and it's time for more math. And the last talk of the day will be given by Pedro Monteiro, and we'll talk about automorphisms and hot structures of Klein hypersurface.
Thank you very much, Georgie, Giancarlo, for the invitation, for the opportunity to be here. It's really nice to see you all. So this is joint work with Victor Gonzalez, Álvaro Liendo, and Roberto Villaflor, all of them participating in the conference in different sessions as well. So first of all, let me start for recalling the very classical construction of the Jacobian of a smooth projected curve, right, over the complex numbers. I should say that everything in this talk is over the complex numbers, not because we are lazy, but because we use actually the topology and stuff like that. So, I mean, it's okay to be lazy, but not today. You have a curve and you think about this curve as a Riemann surface of genus G, let's say. So we have that the first homology group is generated by these guys in blue and red. So you have 2G of them, right? For each hole you have 2 of them. And you know that if you complexify this module, you obtain a C vector space, and this vector space has 2 pieces by Hodge decomposition theorem, essentially. And one of them is exactly corresponds to holomorphic one forms, and it's a G-dimensional vector space. This is very classic, right? And so there is a natural way to look at one of these guys, these curves, and put them, put one of these guys inside of the dual of this vector space, simply by integrating over this curve, right? So you pick a curve, and you obtain this functional that eats one forms and gives you a number. So you have an inclusion of this, and as you may see from the numerology already, This is a vector space of complex dimension G, so real dimension 2G, and inside you have a lattice, so you have you can quotient by this vector space by this lattice, and you get an abelian variety. And this is the Jacobian, right? And the classical Torelli theorem tells you that this is injective, essentially. So I will come back to this later, but this is the whole motivation. I should also say, but I will come back to this at the very end of the talk, that this essentially works every time that you have a Hodge structure, which has like two pieces, one piece and the conjugate one. So you can essentially do kind of the same, and you can get a torus, and it's kind of subtle to have a principal polarization, but I will come back to this later. Okay, so all of this story can be formalized into purely linear algebra, in terms of linear algebra. So let me read a little bit about this. It seems to be a little bit scary, but it's quite simple, right? So it's essentially the homology, right? If you recall that your topology curves, you have some intersection product, right? So you have naturally a bilinear non-degenerate form, okay? So you can do linear algebra inside of this guy. And also when you complexify this module, you have essentially the cohomology with complex coefficients, right, more or less, by concurrent duality. And you have the Hodge decomposition theorem. So essentially you have this vector space that can be decomposed into real subspaces, and they are conjugate to each other, right? And moreover, you have this, if you have a projective variety, you have extra information, because this is embedded into projective space via some ample line bundle, and this information also can be translated into purely linear algebra terms. Let me not enter into details, but the whole geometric picture can be translated into this purely algebraic setting. And of course, the main example that we love is smooth projective varieties, right? So it's essentially a generalization of the first slide, right? You have a stuff, geometric stuff, and you integrate over them. So you have you get into this dual, and by concurrent duality, you can actually arrange this index to be k, right? And moreover, since we're mostly interested in the intrinsic geometry of the variety, of course, there are a lot of information that comes from the ambient space, of the projective space. This is just taking a hyperplane section. So you don't care about this, and you essentially restrict yourself to the so-called primitive cohomology. Okay, this is kind of the setting. Okay, so with this notation, essentially, we can formulate what is called the precise or strong Torelli theorem. So there is a very nice, actually, appendix for an article by Jean-Pierre Serre, where he discusses this for the set. And what we will call the precise or strong Torelli theorem in this talk is kind of the functorial version of the Torelli theorem. This is kind of important. So what is this? So you take two curves, two Riemann surfaces, if you want, and you have these homology groups, and you have a Hodge structure in this, how to say, induced by these guys. And the Torelli theorem tells you, I mean, that essentially the first version that they present to you is that the abelian variety determines the curve, right? This is the Torelli theorem that we learned. But of course, this can be reformulated in terms of Hodge theory by saying that if you have a isomorphism of polarized Hodge structure, right? So you're preserving you have an isomorphism between the polarized associated abelian varieties, not the torrent, but with the polarization, right? Then, essentially the curves are isomorphic. But you can be very precise. That's the kind of the whole point. So if the curves are hyperelliptic, then this morphism comes from a geometric one, so a geometric isomorphism. And if not, then there is an isomorphism, but up to a sign, you obtain the region 1. So this is the precise form of the Torelli theorem. And the idea, more or less, is that this should be more or less true in more generality. Spoiler alert, this is false actually, but there are many situations in which we expect this to be true. So the kind of principle is that if you have some varieties which are in the same connected component of the model space, you can hold maybe that isomorphism between Hodge structures actually comes from a geometric one. This is the, and of course there is a very particular case, and this is a kind of the main, issue in this talk, is to, if you consider of course x to be equal to y, then you are reduced to study automorphisms. So this is what we call the punctual Torelli theorem, because if you think in the modular space, you are like looking at a point, and not isomorphism between two members of the modular space, but only one point, and therefore you're looking at automorphisms of this guy. So the punctual Torelli theorem would say that, of course, by specializing x equal to y, that more or less the automorphisms of the Hodge structure coincide up to involutions, as we already see in the case of curves, with the automorphisms of your variety. This is the expectation. I mean, it's a consequence of the strong Torelli theorem principle. Okay? Questions so far? All right. So let me just give you some historical background on this problem. Well, first of all, for curves is a very classical result by Torelli, the Torelli theorem. For abelian varieties, it's more or less tautological, but it's a very nice exercise to think about what should mean and why it's true. It's a very good exercise. If you want to know the answer, there is a very nice discussion about this in Kondo's book of K3 surfaces. There's a very recent book of, where the strong Torelli theorem is proved for K3 surfaces. But there is also a very nice discussion about that. A very classical result is that this is true also for cubic trifles. This is actually super nice. I can give you a hand-waving proof of this. So in this case, what we have is the following. So you have a cubic trifle, right? So a three-dimensional guy. You can prove that the H3, the homology H3, it also has the same shape as I showed you in the first slide. So you have a vector space decomposed into two pieces, one conjugate to the other. And this is, each piece is 5-dimensional. So you have a 5-dimensional abelian variety. This is the intermediate Jacobi. So you have this guy with the 5-dimensional abelian variety, and there is a very natural divisor that already appeared in this session, which is called the theta divisor. So it's a divisor instead of 5-fold, so it's a 4-fold. Right? And very classical theorems, maybe by, I don't know, by Bouville maybe, Andreotti maybe also studied the singularities of theta divisors. Well, anyways, you can prove that this divisor, which is a 4-dimensional guy, is a cone over a 3-dimensional variety. And guess what? This 3-dimensional variety is X itself. So this is how you recover X from the abelian variety. Yes. Yeah. Okay, so this is more or less the idea, the sketch. So this is also known for cubic fourfolds by results by Claire-Vassin, and for hyperkähler manifolds, which is a higher dimensional generalization of K3 surfaces, and I think they already appeared in Ignacio's talk. So well, this is more or less the picture, and for hypersurfaces, which as we already discussed, they are kind of important, there is a positive answer, but only for generic hypersurfaces. And also, it's kind of very important here that you don't have the functorial version of the Torelli theorem. What you have here is that if you pick random guys inside the modular space of hypersurfaces, they are isomorphic if and only if they have isomorphic Hodge structures. But you don't have the functoriality the strong principle. In other words, you don't know a priori if an isomorphism between Hodge structures comes from an isomorphism of the geometric type. That's the kind of the problem, that's kind of our main motivation. As I said, sadly, this is not what to say? This is not it's a principle because it's not always true. You maybe can hope to be true, but there are many situations in which this principle holds, but sadly, this is not true in general, and there are very important counterexamples, and a lot of geometry involved in the case of surfaces of general type. Here we know that this is actually false, and the first counterexamples were constructed by Catanese and Todorov. The Todorov surfaces, I don't know if these surfaces have a name, but anyways, so this is not always true, so you can also hope to have counterexamples in the case of hypersurfaces. We thought that we were looking at a counterexample, to be honest. I will tell you a story, a funny story at the very end of the talk, maybe. Well, not that funny, I mean, it's kind of sad, but, but anyway, well, it is what it is. So, we were hoping to find a counterexample for the Torelli theorem, a new counterexample. So we said, okay, let's look at hypersurfaces. These are the simplest, I don't know, algebraic varieties from classical algebraic geometry. And we know in this case that all the interesting things happening in cohomology are concentrated in degree n, where n is the dimension of the variety, right? This is just by Lefschetz hyperplane section theory. Okay, on one hand we have this, and on the other hand, we know, this is a very classical result by Matsumura and Monsky, that if you pick a random hypersurface in the modular space, the automorphism group is trivial. So, if you kind of want to produce a counterexample of the punctual Torelli theorem, essentially you should try to look at hypersurfaces with many symmetries, because probably over there you can try to get a counterexample. How? Well, just try to compute the automorphism group of the hypersurface of the Hodge structure and try to prove that they are not equal. It will imply that the strong Torelli is not true. So that was kind of our hope. And so a first natural question is, which varieties you should look at? I mean, which are the kind of the most symmetric hypersurfaces, right? So I should say that there was there are like two possibilities. One is to look at the whole automorphism group, and another one is to look at the one automorphism of the largest possible order. This is kind of the two variants. I should mention, because it's actually very interesting, that there was like a folklore conjecture saying that the most symmetric hypersurface is the Fermat hypersurface, but with few exceptions, right? And there are like two recent works about that. They were posted in the archives, so we still like, well, they have to be checked, of course. But there is two independent works concerning this problem of which is the hypersurface with the largest automorphism group. But okay, let's put that on aside for a moment, and let's take the other direction, which is just fix one automorphism, say of prime order, and ask yourself which is the largest prime that can appear as the automorphism of a hypersurface. And this question was solved by Victor and Alvaro more than 10 years ago, and the answer is the following. If you have a hypersurface of degree d, then essentially the only hypersurface that has a very large automorphism of prime order is the Klein hypersurface. And moreover, you can actually compute the prime, and this is a very funny prime, you know, like it's a generalization of Mersenne primes, it's called Backstaff prime, which are prime of this form. You know, people like trying to find these primes, proving that there are infinitely many of them. Of course, there is a conjecture saying that there are infinitely many Backstaff primes, but we don't know. Yeah, you can try to do it. So because of this, we call these Klein hypersurfaces, which are kind of extremal because they have a very large prime automorphism, we call it of Backstaff type. I should mention also for historical reasons that there are very classical examples of these guys. Probably the most well-known example is the degree 4 curve, right? The Klein quartic, which gives the name of this guy. Klein was studying this, and for this quartic, you can compute this exercise to prove that the prime is actually 7. And there is a very also nice article by Elkis probably on this curve, where all the automorphisms are described, and already Klein knew that the full automorphism group is PSL2 over the field of 7 elements, PSL2 F7. Another very, very nice example of this kind of phenomena is that if you take a cubic of dimension 3, so cubic threefold like Clemens and Griffith consider, this is also an example where this happened. Yeah, I should mention that this is not true for every dimension. There are some dimensions in which you have this inequality. It's not always true. But one dimension where it is true is in dimension 3 and degree 3, and you have the Klein cubic threefold, and the automorphism group is, by the work of Adler, using representation theory, is PSL2 F11, because the prime is 11 in this case. So just to summarize, for curves, you have P equals 7 and the full automorphism PSL2 F7. For P equals 11 in dimension 3 and degree 3, you have the automorphism group PSL2 F11. And the next kind of interesting case, which I'll try to give you, well, I will try to tell you a funny story at the very end, is that if you take cubic fivefolds, you also have one backstaff prime, and this is 43. And something which is very special about cubic threefolds and cubic fivefolds is that both of them have intermediate Jacobians. So in these very particular cases, where you have these backstaff primes, is kind of interesting from the point of view of abelian varieties as well, because you have a naturally associated and abelian variety. I will give you an account of this at the very end of the talk. Okay, so this is so to summarize, you want to try to get counterexamples of Torelli theorem or Torelli principle, to be more precise, and you try to look at really symmetric hypersurfaces. So, well, this is kind of the main theorem of the talk, is that we managed to prove this in the following cases. So you consider these extremal hypersurfaces, meaning that there is a automorphism of higher prime order, and if the degree divides the dimension plus 3, or you have a cubic hypersurface, then the punctual Torelli principle holds. So the automorphism of your geometric guy and the automorphisms of the Hodge structure are the same. So let me tell you that, okay, so this is kind of is sad news, but it's the truth, is that sadly the way that we did it is we computed each of these parts separately and they are the same. So we computed each of these groups and they coincide. So there is so far we don't have a more deep way to prove it, but well, at least we have new evidence on this principle. And I should mention that one of these computations, which is the geometric one, the automorphism of the Klein hypersurface, is kind of interesting on its own. It's based on a method introduced by Contogeorgis, Punen, and Ogiso, which is called the differential method. Let me don't enter into the details, but essentially you pick your equation, and if there are kind of few monomials, you can try to, you can manage to prove that every automorphism, which is linear, by the way, comes from the anti-projective space, is given by matrices which are like permutation matrices, but is, you know, like with ones and zeros, but instead of ones, you have root of the unit. And once you know that, yeah, it's quite easy to compute the full automorphism group. And we have a very effective criterion that tells you that if the shape of your polynomial verifies something, which is very precise actually, you can really check it, then the automorphism group is generated by this pseudo permutation. And that's kind of interesting on its own because it gives a method to compute a lot of automorphisms of many classes of hypersurfaces. This is one part that I want to speak about, and so there is the other part, the automorphisms of the Hodge structure. And in order to do that, we had to extend a previous result by Victor, Alexis Zamora, and Jose Maria Muñoz Porras. They were studying abelian varieties with kind of the same thing, with automorphism of prime order, and the largest as possible. So we had to extend this to Hodge structures because we didn't have abelian varieties, but we had a more complicated Hodge structure, and it actually works. So let me just briefly tell you how it works. The idea is the following. So suppose that you have an automorphism of your Hodge structure. If you want to fix ideas, it's not that wrong to think of the case of abelian varieties. So yeah, if you want to fix ideas, think in abelian varieties. So we have the following. So you pick essentially the kernel of your automorphism minus the identity. This, of course, measures the fixed points of sigma, right? This is just the fixed point, right? And this is also defines a Hodge structure. And you can do the same essentially with all the powers of your automorphisms. And this is a sort of artificial but useful way to mod out to kill all the fixed points, right? You just mod out by the kernel of these guys. This is a Hodge structure, and when you extend your scalars to the complex numbers, you have automorphisms. Automorphism over the complex numbers that you can understand using linear algebra, and you can show that since there are not fixed points, and since this is a finite order, then all the eigenvalues of this induced automorphism are primitive root of the unit of 1, and thus the characteristic polynomial has to be a power of the cyclotomic one. And just by degree computations, you can actually compute which power of this cyclotomic polynomial is. And a very naive observation, but it's quite useful, is that since this has to be an integer, right? the phi of m, Euler's phi function of this number m has to divide this dimension, which is the dimension of h minus the dimension of the fixed points. So in the particular case where m is a prime, you know that this is p minus 1. So the maximal number that you can get is this one. And this is the definition, the right definition in the context of general Hodge structures. Let me just say that if the action has no fixed points, so this h0 doesn't appear in the picture, and then, of course, you have h plus 1. And in the case of abelian varieties, you have, remember, two pieces conjugate to another, and the dimension is g. So you have 2g plus 1. And this was the original definition of principally polarized abelian varieties. And this is just a very naive but useful generalization to more general Hodge structure. Okay. So the thing is the following. In this particular case, and to be completely honest, what we had to do is to pick any good book on abelian varieties. I don't know, Pirkenhacker Lange, or also the book by Shimura Taniyama. And we kind of see what we had to modify. And essentially, we observed that in this case, the Hodge structure decomposes of the direct sum of eigenspaces, and each eigenspace is one dimensional. This is kind of the fundamental thing. And moreover, this decomposition into this spectral decomposition is compatible with the Hodge structure. In other words, each of these vector spaces appearing in the Hodge decomposition is also sum of these eigenspaces. Therefore, there is a natural, since you have the primitive p root, since you have the p root of unity, each of them is an eigenvalue, you have this package of eigenvalues, and they correspond. I mean, there is another partition induced by the Hodge decomposition. So essentially, we prove that how to say, the automorphism of the Hodge structure is more or less the automorphism that fixed this package. And that's kind of the how to say, the way how we calculated the automorphism group. More or less. But, well, here's the precise statement. So, this is kind of the main result actually of the talk, and it's the following. So, first of all, we have this notion on the geometric side, right, of the extremal guys, this hypersurface with a very large prime order automorphism, and these guys, which are geometric, have this Hodge structure. And we have two notions of extremality, and well, you have to prove that they're the same. I mean, and we have to do it, and we have to check more or less by hand that this is actually an extremal Hodge structure. And once you know that, the idea is the following. The idea is that you have this package of, I mean, this partition, right, of that I showed you before, and there are two naive automorphisms of the Klein hypersurface. Let me show you the shape of the hypersurface here. So there are two naive automorphisms. The first one is kind of obvious, is just change the variable, right, the cyclic permutation. This is one naive automorphism. And there is another one that you can actually compute, which is the diagonal automorphism. And you can actually compute the order, and actually it's this. And so we proved using this differential method that I didn't explain, that these are essentially the only two ones, and they generate the full automorphism group. It's the symmetric product of these two guys, of this automorphism of order, the number of variables, and ZP. These are
semi-direct probe.
Yep. Yeah, I should mention, we prove it for almost all cases, except for K3 surfaces. Actually, yeah, we spoke with Michela, and after some discussions, we realized that in the case of K3 surfaces, the automorphism group has to be infinite. But that's the only thing we know, because essentially the Picard number is maximal, and then there are some results by Shioda Inose that says that K3 surface with maximal Picard rank have infinite automorphism group. That's all what we know. Okay, so, well, just more or less to finish this part of the discussion, the thing is the following. So you have a Hodge structure, and one wonderful thing for hypersurfaces is this famous theorem by Griffith that gives you an explicit basis for do computations. Like it's really, really explicit. And actually, by the way, we think that we should be able to prove this kind of theorems in other contexts where you have some variants of this Griffith's basis theorem, like hypersurfaces in Grassmann and stuff like that. Well, anyway, so if you compute using this basis, the theorem, I mean the punctual Torelli principle, which says that the automorphism group is the naive one, reduces to this elementary number theory thing. It's kind of funny. This is kind of a statement for for Olympiads or something like that. It's purely number theory stuff. The more complicated stuff that appears in the statement is FP probably. But sadly, we're only able to check this for cubic hypersurfaces using some very combinatorial argument using graphs and stuff like that. We really hope that there is a more elegant proof. Of course, we try to check it on computer, and it's always true. But we only have a proof for cubic hypersurface and for this hypersurface where the degree divides the dimension plus 3. And the condition, let me just read it for the sake of completeness, is that you look at this kind of minus 1 minus d adic expansion, and such that the coefficients are bounded, and the sum is this number. If you have seen the Griffith basis theorem, this should be familiar for you. This is kind of the thing that appears when you read the theorem. So you have to check that if you have this package of integers mod p, the only invertible element of the field Fp that preserve this package are multiples of 1 minus d. That's the condition. Is how to say? It's pure elementary number theory, and sadly we are only able to prove it for cubic hypersurfaces. But still, there is a nice consequence of this, that this implies actually the most geometric version of the punctual Torelli theorem, namely the one involving intermediate Jacobians. Why? Because it's a very old result by Deligne and Rappaport that the only hypersurfaces, smooth hypersurfaces, that admit intermediate Jacobians, recall that means that the cohomology of degree n, when n is the dimension, is the direct sum of two conjugated vector spaces, and therefore you can construct a torus. The only ones are smooth cubic trifles, and we know that the Torelli theorem is true by Clemens and Griffith. Smooth quartic trifles and smooth cubic trifles, fivefolds, sorry. And they have abelian varieties associated with abelian varieties of dimension, the half of this, 5, 30, and 21. So you have 3 nice abelian varieties, and our results implies that in the last 2 cases where we don't know the Torelli theorem, the automorphisms are the same. In this case, it's just applied, just this case, d equals 3. And for d equals 4, you do it by hand. I mean, it's a finite list, you can actually check it, and it's true. So it's not a very deep proof, I mean, how to say. It involves a lot of nice math, but at the end, you compare 2 groups and they are the same. But gives you a new evidence of the Torelli theorem in this case. I should also mention, like the funny slash sad story, we thought at the very beginning that we were like heading into a counterexample of Torelli theorem for a smooth cubic fivefold. Why? Just because of numerology. Because first of all, this number 43 or 21, if you want, is very, very special. This is one of the imaginary quadratic extensions that has class number equals to 1. There are finally many of them, and they're classified. It's a very typical exercise on algebraic number theory. And one of them is 43, and there is an extremely nice result by Benama and Bertin, telling that in this case, there is only one abelian principally polarized abelian variety with automorphism groups PSR2 F43. And as I told you before, we have the Klein quartic, whose automorphism group got the same thing but with 7. We have Adler result on the Klein cubic trifle, saying that you have the same automorphism group but with 11 instead of 43. So, of course, the naive guess was, well, of course, the automorphism group of this guy, the Klein cubic fivefold, was this one. But at the end, it wasn't the case. This, by the way, this would have implied that how to say? This would imply that the 2 groups are different, just because you can essentially analyze very precisely all the representations of this group. They don't appear MP6. By the way, this will be this is a fake proof, right? We would have that the Jacobian have this automorphism group, and this automorphism group cannot be realized in P6. But this is not the case, and they're actually equal. But at least this raises a natural question, is that in this modular space of abelian varieties of dimension 21, we know by a fact that there is a very special guy, a unique abelian variety with this automorphism group. We know by the computations we did before that it's not the Jacobian of a cubic fivefold, and just because of the, I don't know, the Hurwitz bound on the size of automorphisms, you know that it cannot be the Jacobian of a curve. So a very natural question is there a modular interpretation of this abelian variety? Is the Jacobian of, or the prime variety or whatever of something? I don't know. But I think it's a nice and interesting question in this setting. So thank you very much for your attention.
We have time for questions, fake questions.
Fake proofs.
Dimension of the inside of the bullet space, like one of the intermediate.
Sorry, yeah, I have a computer. I don't remember by heart, but it's yeah, but it's smaller man.
It's small.
Yeah, yeah.
Do you guess that just because why you thought it was I didn't
No, because this Klein hypersurface seemed to be a kind of different automorphism group, and at the very beginning we thought that it was the case. Yeah, but it wasn't the case at the end. Yeah, they weren't a hypersurface. As far as I know, yeah. And maybe I should mention also that there is some other kind of positive evidence to the Torelli theorem in these two cases. One is by Collino and other by Letizia. And they kind of prove that there is some, when the hypersurface is generic in the modular space, there is some Abel Jacobi map which is an isomorphism. So, yeah. But also for generic ones, so we don't know for a particular one.
Other questions?
Oh, we're saying generically we didn't have strong added vacancy, right?
So, but the problem is that for generic hypersurfaces, the automorphism group is trivial, so it's kind of automatic. The punctual one. Yeah.
Okay, let's thank
Thank you. Sí. Sí. Gracias. ¿Algo más? Sí, esa cosa.
No, muchas gracias. Gracias.